So let's talk about page 3 of our week 4 concept check packet over ionic compounds. So the first thing we want to do is make sure we're all on the same page with this idea of being isoelectronic with a particular noble gas. Again, as we discussed earlier, right, it's all about the octet rule. Things are either trying to lose electrons out of their current valence shell to get back to the previous filled shell, or they are trying to fill up their current valence shell to 8 electrons, right? The octet rule. And in doing so, they can look like a noble gas, which is a stable electronic situation. And so let's talk about our first example here. And the first thing that we want to say is remember that isoelectronic just simply means the same number of electrons. So in our first box, we're looking at anions. And so remember, when you see anion, that means a negative charge that comes through the gaining of electrons. And from what we talked about on page 1 and page 2, right, we know that that's going to mean a non-metal. And then, of course, krypton, you can go to the periodic table and see that it has 36 electrons. So when you're looking for something that's going to gain electrons and look like krypton, you want to look at nonmetals right near krypton, right in front of krypton. And so what element comes right before krypton? Bromine. And so bromine is element 35. So it starts off with 35 electrons. And so to look like krypton with 36 electrons, you're going to have to gain 1 electron. Remember, that's going to give it a negative charge. Remember, when it comes to counting electrons, the charge is kind of opposite of what you're doing, right? If you're adding electrons, you're getting a negative charge, again, because electrons have a negative charge themselves. Another possibility would be selenium. So selenium starts off with 34 electrons. If you want it to have 36 electrons, it's going to have to gain 2 electrons and become a 2- ion. Both of those are isoelectronic with krypton. Now we can do the same thing with cations, right? Cations have a positive charge. They're formed when something loses electrons. And so again, we want to be thinking about metals. And so if we're looking for neon, we're talking about something with 10 electrons. And so when you start to look at metals that are going to become isoelectronic with a specific noble gas, you want to look right after that noble gas. So in the case of neon, look at element 11, sodium. Sodium starts off with 11 electrons. So to get to 10 electrons, it's going to have to lose 1 electron. And that gives it a positive 1 charge. Or, right, you could deal with magnesium. That starts off with 12 electrons. To get to 10 electrons, it would lose 2 electrons and become a 2+ ion. Or we could even do aluminum. Aluminum is element 13 with 13 electrons. If it loses 3 electrons, now it's down to 10 electrons and has a 3+ charge, and it's isoelectronic with neon. Again, like we said on page 1, they still have the same number of protons, so they're still the same elemental, the same element, have the same elemental identity, but they have now changed their charge because they no longer have a balance between protons and electrons. All right, let's look at our second part here, where we're looking at difference in electronegativity. So I'll always provide electronegativity values for you. So when you go and you look them up, right, sulfur is 2.5, sodium is 0.9 based on our table there, 3.0 for chlorine. In the case of oxygen, we have 3.5, fluorine is 4.0, iodine is 2.5, bromine is 2.8. And so when you go to take the difference in electronegativity, what you want to do is subtract the two numbers, and you want to do it higher value minus the lower value. And so in the case of sulfur and sulfur, it doesn't matter. They're both 2.5. The difference is 0. In the case of chlorine and sodium, you want to take chlorine's 3.0 and subtract sodium's 2.9 or 0.9 to get a difference of 2.1. Same thing here. I'm going to take the 4.0 minus the 3.5. Doesn't matter what order they're listed in. You want to think of this as kind of the absolute difference. And so in my final one, I take 2.8 minus 2.5 to get a difference of 0.3. And then what we want to do is just compare that to kind of our guidelines. And these guidelines are not going to be right 100% of the time, but again, this is a prediction. And so predictions don't always come true, but this is a pretty good predictor. And so if our difference in electronegativity is less than 0.5, we're going to call that non-polar covalent. And we'll learn more about non-polar covalent bonding when we get into talking about molecular compounds a little bit more. But the idea here is the two atoms are close enough in electronegativity that they can't, when they go to fight over those electrons, neither one's strong enough to really cause much of a difference. And so they're basically sharing, they end up sharing those electrons equally. Now, once you hit 0.5 or greater, but less than 2.0, you have what's called polar covalent. And so the fact that it's covalent means they're sharing, but now they're not sharing equally, right? One of them's stronger, it's kind of, you know, has those electrons more often than not, but it can't quite pull them away. And then once we hit that 2.0, right, if our difference in electronegativity is greater than or equal to 2.0, right, that's when we have an ionic situation. And that's when we get a transfer of electrons from usually a metal to a non-metal. And so if we compare our values to these three categories, hopefully what you see is that no difference is nonpolar, a big difference is ionic, a medium difference is kind of polar covalent, and then you can have a difference but not be very much and still be considered nonpolar. And so notice that only B has a metal and a non-metal. That's usually how you end up with an ionic situation, right? The other three involve two non-metals, and that's going to be what we're going to deal with most of the time when it comes to molecular compounds. All right, let's move on to page 4. And so, again, you had an exercise over this, you had a lecture quiz over this, so hopefully you're feeling pretty confident about electronegativity difference.